In this video, we're going to cover section 1.10, perturbation relaxation methods. As mentioned in the previous video, the forward and backward rate constants for reactions approaching equilibrium can be determined by monitoring the evolution in reactant or product concentrations as equilibrium is approached, and by measuring the concentrations at equilibrium. So one question we must ask ourselves is, what if the initial conditions for the reaction cannot be controlled? For example, what if it is impossible to sequester the reactants such that initiation of the reaction at a specified time is impossible? Well, in such situations, if one can perturb the system by changing temperature, pressure, or concentration, the system will no longer be at equilibrium and as a result will evolve until a new equilibrium is established. If the perturbation occurs on a time scale that is rapid compared to the system relaxation, the kinetics of the relaxation can be monitored and related to the forward and back rate constants. This is the basis for the perturbation relaxation methods. The temperature jump or T-jump method is by far the most common method used in chemical kinetics to study reactions that are approaching an equilibrium. So let's consider again the following reaction, in which the forward reaction A to B is first order in A, and the back reaction B to A is first order in B. And you'll recall that the forward and back rate constants are K1 for the forward and K-1 for the back reaction. So next, if we can induce a rapid change in temperature, and we can do that via a few ways. We can use laser excitation, laser pulse, or in some cases an electrical discharge to change the temperature of your sample very quickly. If we can do that such that the forward and back rate constants are altered in accordance with the Arrhenius expression, a new equilibrium is established. And so we will use these superscripts plus to indicate that the rate constants correspond to the conditions after we've changed the temperature, after the temperature jump. So following the temperature jump, the concentrations of reactants and products will evolve until new equilibrium concentrations are reached. So at the new equilibrium, the differential rate expression for the reactant is equal to 0. And we can equate that as well to the two terms, now expressing that superscript plus to indicate that these are the new rate constants after the temperature jump has occurred. In doing so, these two terms will be equal to each other at that point. Now again, the subscripts on the reactant and product concentrations represent the new equilibrium concentrations after the temperature jump. The evolution of reactant and product concentrations from the pre-temperature to post-temperature jump values can be expressed using a coefficient of reaction advancement. Specifically, let the variable xi, shown here, represent the extent to which the pre-temperature jump concentration is shifted away from the concentration for the post-temperature jump equilibrium. So what we're saying is that the concentration of A for the post-temperature jump equilibrium is equal to the concentration of A pre-temperature jump minus this particular advancement of that reaction. And as we see a change in the concentration of A, we'll see a concomitant change in the concentration of B, but of opposite sign. Now, immediately after the temperature jump, the concentrations will evolve until equilibrium is reached. Using this idea, the differential rate expression describing the extent of reaction advancement is as follows, where we have d xi dt is equal to minus K1 plus times the concentration of A plus a K minus 1 plus times the concentration of B. So in a sense, what we're doing is we're following that change, that advancement of the reaction, as opposed to following a change in the concentration of A or the change in the concentration of B. It's easier to follow one variable than it is to follow two variables. So we are following that change, xi. Notice in this equation that the forward and back rate constants are the post-temperature jump values. If we substitute into this differential rate expression, we get the following. So if we take the concentration of A and B and we substitute in for the expressions that we defined on the previous slide, we're left with the following. So we substitute in xi plus the concentration of A at equilibrium and minus xi plus the concentration of B at equilibrium. Now, if we multiply through and collect like terms, we're left with the following expression. So we have our same two terms as shown above, but now with our subscripts equilibrium to represent that new equilibrium concentration for both A and B. And we have this term here. Now at equilibrium, these first two terms will cancel because they're equal to one another, and that will give the following. d xi dt is equal to minus xi multiplied by the sum of the two rate constants K1 plus K minus 1 plus. So we refer to the inverse of that sum of rate constants as the relaxation time tau. So the relaxation time tau is defined as follows. It's the inverse of the sum of the two new rate constants as that new equilibrium is approached. So using this definition of the relaxation time leads to the following solution, where now we can substitute in for the sum of the rate constants with 1 over tau. So d xi dt now becomes equal to minus xi over tau. If we rearrange this expression slightly by bringing xi down and dt up, in integrating both the left and right hand sides with their respective limits, we're left with the following integral. And this is the same integral that we've seen for first order reactions. So no surprise that after we carry out the integration of both sides, we're left with an exponential form, where xi is equal to xi naught e to the minus t divided by tau. So this shows that for this reaction, this temperature jump experiment, the concentrations will change exponentially, and that the relaxation time is the time it takes for the coefficient of reaction advancement, xi, to decay to e to the minus 1 of its initial value. And that's the general definition for a relaxation time or lifetime. It is 1 over e times the initial concentration of your reactant species. The time it takes for that to occur is often referred to as either the relaxation time or sometimes simply the lifetime of that species. And we'll see more of that when we look at absorption in fluorescence spectroscopy. So what we've shown is that the time scale for relaxation after the temperature jump, it is related to the sum of the forward and back rate constants. So if we have this information in combination with the equilibrium constant given by a measurement of the concentrations of A and B at equilibrium, with this information, we can determine the individual rate constants. And so what I have here is a couple diagrams representing the temperature jump or perturbation relaxation method. In this example, we see that we start at some temperature T1, where we have a particular concentration of A. And then after the temperature jump has been induced, so after the laser pulse comes in and warms up the sample, or after the electrical discharge, we're going to see that we've now disrupted that equilibrium. We've increased the temperature of the sample, so therefore we're going to approach a new equilibrium at that new temperature, which in this figure is T2. And so we can see that this exponential relaxation to that new equilibrium, this is the information we're using. This is what we're fitting to determine the sum of the two rate constants. We can't determine explicitly what K1 plus or K minus 1 plus is. We can only determine the sum from this exponential growth as shown here or exponential decay, just depending on the thermodynamics of the system. But if we know what the equilibrium constant is at the new equilibrium, that is, what is the ratio of concentrations of A and B at T2, we know that that is equal to a ratio of the rate constants. So if we know the sum from the exponential curve and we know the ratio from a steady state measurement, we have two equations, two unknowns. We can solve for K1 plus and K minus 1 plus respectively. Here's just another figure describing the perturbation relaxation method where we have the pre-jump concentrations for both A and B, that is concentrations of A and B pre-temperature jump. And then following the jump, so T equals 0, we have the laser coming in or the electrical discharge, which raises the temperature or pressure of the system. And then we watch how the new equilibrium is established. So in this particular instance, we see a decay of the concentration of A with time. So as the new equilibrium is being approached, we see a decay from A equilibrium pre-jump to the A at equilibrium post-jump. Similarly, the concentration of B in this scenario is going to increase with time at the expense of A as it decays. You could fit either of these exponential curves to get the sum of those two rate constants, which we describe as that relaxation time. So 1 over the sum of the two rate constants, that is the forward and back rate constants, that is equal to our relaxation time. So if you have any questions about the perturbation relaxation method, by all means, send me an email. Thank you.